In this presentation, I'm going to talk about the research titled Design of an Autonomous Robot as a Base Platform for Research of Cyber-Physical Systems that was conducted at the Universidad de las Fuerzas Armadas ESPE. The authors are Luis Escobar, David Loza, Alexander Carrera, Fabricio Quinaluisa, Andrés Tuapanta, and Henry Rivera. First, here is a brief summary of contents. Motivation, that means what the goals were. Cyber-physical system, what they are and how they were used. Design and construction, where is explaining how the robot was built. Experimentation, in this section is presented all the experiments performed in the platform. Conclusions, here the results obtained are presented. Nowadays, there are commercial and research mobile robots that recognize its surroundings, have an autonomous navigation, also obstacle avoidance. That is because they use complex algorithms. These robots have purposes such as security and defense, services for vulnerable people, education and research. However, due to the high degree of autonomy, it is difficult and expensive to obtain one in developing countries such as Ecuador. In this context, the goals were set. It is need a platform that recognizes its surroundings, able to do an indoors reactive navigation with an autonomous charging and path planning. Finally, all the systems should be scalable and stable, but with a low cost. According to Bricknell, mechatronics and CPUs are two different perspectives of a global concept called system. Mechatronics is considered here as evolution of electromechanic products, and CPUs comes from a cyber system evolution. This helps to explain why there is a strong software and communication dimension in CPS. A cyber physical system approach ensures a low cost by increasing the capacity of sensors and actuators. Moreover, it also gives the opportunity to use wireless communication and increase bandwidth. A CPS complements a mechatronic design due to its advantages, such as scalability, stability, robustness, among others. With this information, it is necessary to know what low cost is. Some commercial robots are compared in the table shown. The parameters of comparison are the characteristics before mentioned. Here we compare the robots Kabuki, RB1, RB2, Freight, and Tortable Theory that give a hint of how the design should be and how money it should cost. A configuration with capacity to climb small slopes up to 10 degrees and with the capacity to navigate through different floors as carpet or ceramic was designed. Differential locomotion with a caster wheel of 5 cm was used to allow the movement on irregular surfaces. The structure of the mobile robot is circular in order to avoid closer obstacles, especially when it turns over its own axis. The robot has a maximum diameter of 48 centimeters and a height of 60 centimeters, which gives the ability to go through doors and thigh holes. The mechanical design allows the robot to climb obstacles with a maximum height of 6 centimeters. The maximum speed of the robot is 1.5 meters per second. The maximum payload is 5 kilograms and its own weight is 10 kilograms. There are two batteries connected in series that give the robot 24 volts necessary for the motors. Here is shown the process of the chassis construction, then sensor distribution and placement, and finally it is designed the charging station and the hold-up mechanism. To ensure the mechanical capabilities of the robot, computer-aided emulation of all the structures were carried out. In the software development, the mobile robot software was embedded into the onboard computer Raspberry Pi 2. It has connected the RP leader that communicates with the microcontroller. The robot is connected to an external computer via Wi-Fi in a master-slave configuration based on TCP/IP protocol to connect between computers. The onboard computer executes all the functions over the motors and sensor data. The master computer executes the simultaneous location and mapping (SLAM), navigation and planning trajectories, and auto-positioning for the charging station. A navigation algorithm with obstacle avoidance and trajectory planner has been developed. The main goal of this algorithm is to navigate from the initial point to a goal, dodging obstacles and people present in the maps. The dynamic window approach and the trajectory planner 8* make it possible. The dynamic window approach algorithm has a local planner that requires the robot know its position all the time. For this reason, an adaptive Monte Carlo localization particle filter is used to adjust the robot position in real time. The action of the dynamic window approach algorithm and its simulated trajectories are shown in the map. The action of the RP leader with the information collected by the ultrasonic sensor are updated periodically. The sensor locates the position of the obstacles and the algorithm discards trajectories where a collision is detected. A search for the best command of velocity and acceleration with obstacle avoidance and minimum travel distance is done in real time. The platform has the ability to recharge autonomously. The machine and the docking station have two contact points that allow to charge the robot just by the correct placement. A system with 3 infrared emitters was implemented in the docking station and 4 infrared receptors in the platform. To ensure the charging cycles was autonomous, the information about the battery level is obtained by a circuit in the robot. The first experiment was to test the mapping velocity. The objective was to get a clear map of an area with the measured velocity. To carry out this experiment, 4 velocities were settled down: 0.5 meters per second, 0.35 meters per second, 0.2 meters per second, and 0.17 meters per second. As it is shown in the figure, C and D were good options, but in a error analysis, the best velocity was 0.17 meters per second because it has the lowest error. The second experiment means to the path planning and navigation test. In this experiment, the robot has to plan a path to the goal. If there is any obstacle, it will recalculate its trajectory. Finally, the real position is compared with the goal. And as can be seen in the table, the maximum error was 4.53%. Finally, the last experiment was to test the auto placement in charging station. In this experiment, it evaluated the capacity of arrive to the docking station even if the robot is misaligned. In this table, 4 states of the platform were tested, and even in the worst case, the result was good, and the robot was charging. The conclusions are: the robot can make curved and straight paths at 2 rads per second and 0.69 meters per second respectively. The maximum payload of the robot is 5 kilograms, and the energetic cost is 6.34 amperes. The robot is able to get a good autonomous self-positioning in the charging docking station by infrared sensor use. The robot can mapping with a maximum error of 3.56% with a velocity of 0.17 meters per second. It also has obstacle avoidance in base of a trajectory planning using dynamic window approach. And finally, as a CPS platform, it is shown that it has the capacity to connect through IoT protocols and be used as part of more complex systems in the future. Thanks for your attention. If you have any question, here is our contact information.